On February 23, 1997, at 3:30 p.m. Eastern Standard Time, a Defense Support Program satellite lifted off from Cape Canaveral Air Station, becoming the first satellite to be launched aboard the Titan 4B rocket. Since the first DSP launch in November 1970, DSP has been one of the longest-running and most successful military space programs, serving the nation for well over 30 years. Over the years, 5 upgrades have improved the 5,200-pound satellite's capability, survivability, and life expectancy without major redesign or interruption in service. These improvements doubled communication links, expanded data rates, enhanced hardness, added redundancy, increased power to 1,275 watts, and reduced single-point failures. DSP satellites are a cornerstone of our national defense capability, performing their critical mission as the spaceborne segment of the North American Air Defense's Tactical Warning and Attack Assessment System. The satellites use infrared sensors to detect heat generated by strategic and tactical ballistic missile launches and nuclear explosions. During Operation Desert Storm, DSP satellites were successful in helping the United States and its allies identify strategic and tactical threats. The satellites detected the launch of Iraqi Scud missiles, providing a timely warning to civilians and coalition forces in Israel and Saudi Arabia. Since Desert Storm, improved ground processing has significantly enhanced the DSP's tactical warning capability. The DSP spacecraft is assembled and tested at the Northrop Grumman Space Technology Facility in Redondo Beach, California. Satellite buildup is completed with the installation of the primary and secondary sensors built by Northrop Grumman Electronic Systems and Sandia. The satellite is shipped to the Cape and prepared for launch by a team of Air Force and contractor support personnel. Northrop Grumman is responsible for providing a trained team to support launch and early on-orbit testing, EOT operations, ensuring the health and safety of the spacecraft throughout the scheduled 30-day EOT period. The purpose of the on-orbit testing is to deploy, test, configure, and perform on-orbit calibration of the DSP satellite prior to operational use by the Air Force. In final preparation for launch, propellant tanks are loaded and pressurized. The reaction wheel is backfilled with dry nitrogen, batteries are fully charged, and all ordnance is installed and connected. During the countdown sequence, various test and operational functions are accomplished. At T-minus 20 minutes, power is transferred from a ground source to vehicle internal power. At T-minus 0, the flight phase begins with solid rocket motor ignition. Following liftoff and after clearing the tower, the booster begins a slow roll. Ascent continues with a pitchover maneuver to downrange. Approximately 2 minutes into the flight, the Stage 1 engines ignite. At 2 minutes 23 seconds, the solid rocket motors separate and fall away. Approximately 4 minutes into the flight, the payload fairing is jettisoned. The booster and its payload are now beyond the sensible atmosphere, but do not yet have sufficient energy to achieve orbit. At 5 minutes and 21 seconds, Stage 1 separates from Stage 2 using the fire-in-the-hole technique when the Stage 2 engines ignite. With this burn completed, a low Earth parking orbit is established. At 8 minutes 54 seconds, Stage 2 separates from the inertial upper stage when 4 core retrorockets on Stage 2 fire and the structural adapter is severed by pyrotechnics located in the aft skirt. At 1 hour 13 minutes into the flight, the IUS fires the first of 2 solid rocket motors, placing the IUS and DSP into transfer orbit. During the 6-hour coast in transfer orbit, the IUS performs a thermal roll to provide even distribution of solar heating. A final insertion burn and separation from the IUS places the DSP-1 satellite into a circular, near-equatorial geosynchronous orbit. Sensing separation from the IUS, the satellite's solar paddles are deployed. The IR sensor, attitude control system, and reaction wheel are powered on, and over the next 8 hours, the counter-rotating force of the reaction wheel is used to establish a nominal satellite rotation. Subsequent satellite control is the responsibility of the 50th Space Wing's 1st Space Operations Squadron at Schriever Air Force Base and the 21st Space Wing's 2nd Space Warning Squadron at Buckley Air Force Base. Technical support is provided by Northrop Grumman and Sandia personnel at the control sites and factory test facilities. At a point in orbit approaching satellite dusk or dawn, the onboard control system is configured for sun acquisition and Earth search. The sun sensor sweeps the sky as the satellite rotates, supplying control signals used to align the satellite normal to the sun line. A satellite rotation rate about the sun line is then established, providing an Earth search pattern. Satellite Earth pointing is achieved, and attitude control is switched to the forward-facing Earth sensor. The satellite is configured from course to fine pointing modes. At this point, the sun protector is ejected from the IR telescope. Most of the satellite subsystems are initialized, tested, and configured for normal mission operations. Continuous state of health monitoring is performed, and sensor calibration is initiated along with the testing. The satellite is spinning with its spin axis nominally pointed along the local nadir. The spin allows the DSP sensors to sweep their fields of view, to uniformly distribute the thermal load, and to time-share one single axis attitude control system to effect two-way Earth-pointing control. The IR telescope collects IR energy, focuses that energy, and converts it into electrical signals. These signals are digitized, processed, and formatted for transmission to the ground. Spinning silently over the globe, DSP waits, watching for the heat signatures associated with missile launches. Though few in number, IR events potentially represent the worst kind of nightmare. These signals are the first to alert us to impending missile attacks. The heat of missile plumes illuminates the cryogenically cooled focal plane array of DSP, triggering an elaborate warning system honed over the past 30-plus years. The cooled detectors of DSP view the Earth in a nadir-pointing clockwise swath at 6 RPM, revisiting areas of interest every 10 seconds. Once an event is detected, the DSP ground segment sends tactical information to many users, including the North American Air Defense Command and to theaters of operation. Detectable IR events last only a short time during boost phase. DSP continues to track the event with each pass. Data on the estimated launch point is sent to forces dedicated to searching out and neutralizing launch capabilities. Additionally, each pass of the sensor narrows down the direction of flight and missile type, and by the duration of the burn, the estimated point of impact. DSP continues to be our nation's first line of defense against missile attack. The DSP team has much to be proud of, having produced and operated this critical system for well over 30 years. DSP, the Silent Sentry.